Hi there, my name is Caitlin, and in this video, I'm going to be walking you through the great wide world of routing tables. Let's say you want to send an email to your friend who lives across the country. How does your email get to your friend's computer? Well, it certainly does not go straight from the router in your living room to the router in theirs. It needs to pass through many routers to get there. So how do the routers know which path to take? Inside of each router, there is a routing table. Routing tables help routers determine where they should send information. Let's go through the makeup of a routing table together. It is comprised of rows of routing information. Each row is a possible road that the router could send the information down. Now let's go over the columns. The network/subnet column lists the possible networks that the router could send the information to. The mask and prefix column lists the subnet mask. The metric column lists a metric involved in sending the information down that path. It can mean a lot of different things, such as cost or speed. The interface column lists the interface or port of the router that it must send the information from to get to that path. And finally, NHR, or next hop router, is the next router that the information will be sent to. Now that we know how the routing table is set up, let's try to fill one out. To do this, we're going to use this cluster of networks and routers as an example. Let's say we wanted to create a routing table for router A. Each of the 4 networks shown in this example, represented by the bubbles outlined in dotted lines, would have their own row in the routing table. I'm going to start with the network in the lower left corner. Let's go ahead and enter the numbers shown into the first column of our routing table. Next, we are going to enter the subnet mask. Because the prefix is 24, we know the first 24 bits are going to be represented by 1s, creating the mask 255.255.255.0. The metric we are going to be using in this example is the number of hops between routers it takes to get to that network. In this case, we are not hopping to any other routers, so the metric will be 0. Like I said earlier, though, the metric can be one of several different methods used to help the router make its ultimate decision of where to send the information. If the metric was cost, you would obviously want to choose the pass with the lowest value. Alternatively, if the metric was speed, you would want to choose the pass with the highest value. The interface or port of the router that the information needs to leave from to get to the network is 1. And finally, there is no next hop router because the network is directly connected to router A. Therefore, instead of writing a router here, we will write local. Now let's create a row for the network at the top of the diagram. Enter the network IP address. Then we enter the mask, which is 255.255.0.0 because the prefix is only 16 this time. Now, this path is different from the last one because the information needs to hop one time, from router A to router B, in order to get to the desired network. Therefore, the metric will be 1. Enter 2 in the interface column because the information would lead from router A through interface 2. And the next hop router is B because the information needs to hop to router B before it can reach the network. Now, let's write in the information for the other 2 networks. Is our routing table finished? We have entered all of the networks in the diagram into the table, but we forgot one very important row, the default row. The default row tells router A where to send the information when the destination IP address of the packet does not match any of the existing rows. The network IP address of the default row is always 0.0.0.0 because it will match any destination IP address that may come through the router. The mask will also be 0.0.0.0, and the prefix will, of course, also be 0. In this case, I'm going to assign router C as the default router, so I can enter 1 in the metric column and C in the next hop router column. And finally, enter 2 is the interface. Now our routing table is finished. But how does the router use the table to decide where to send the information? Let's say we have a packet of information with a destination IP address of 128.196.34.2. The router will begin by masking the packet's destination IP address with the mask in each row, taking the result and comparing it with the network/subnet value in that row. If the result matches, the router will add the row to the list of matching rows for that packet. If the result does not match, the router will ignore the row. In this case, it looks like rows 2, 4, and of course row 5, the default row, match. If only the default row had matched, router A would have sent the information to router C. If only one other row had matched, router A would have sent the information to that network. But because there were multiple matches besides the default row, the router will next examine the length of the matches. The row with the longest matching network/subnet address is selected. In our row, network 4 is the longest match, and therefore it is selected. This means that the information will be sent to the next hop router C. If there had been multiple matches of the same length, the router would select the row with the best metric, meaning the lowest cost, highest speed, or fewest number of hops between routers. And there you have it. The great wide world of routing tables and all of its mysteries have been explained. So the next time you are planning on sending an email to a friend, think about the routers your email is being sent through and the complex decision-making they are doing in less than a second. And just know that it is all made possible by routing tables.